Hello everyone, my name is Alex and I'm a PhD student at Imperial College London, and welcome to my short talk on tree ensemble kernels for Bayesian optimization with known constraints over mixed feature spaces. And let me start with a quick introduction into Bayesian optimization. The goal in Bayesian optimization is usually to optimize some sort of unknown black box function for which we can query a new input at every iteration and observe its output. And since we don't know the functional form of our black box function, Bayesian optimization deploys a surrogate model that is trained on the available data and learns the black box behavior. The mean of the surrogate model gives us a good idea of where we can find good black box values, and the surrogate's variance metric indicates which inputs we have to further explore to better understand the black box behavior. And in Bayesian optimization, this is called the exploitation-exploration trade-off that is captured in the acquisition function. The here proposed algorithm contributes to the existing literatures by allowing for explicit input constraints, global acquisition function optimization, and effective handling of mixed feature spaces. And to give an example where this is relevant, in neural architecture search, we may want to tune hyperparameters of a variational autoencoder with the goal to minimize some sort of loss of a validation dataset. And as you can imagine, this problem is subject to certain architecture constraints. And to tackle this challenge, we deploy the kernel interpretation of tree ensembles, which I'll explain in the next few slides. So besides many other advantages, tree ensembles have the advantage that they can naturally handle various data types and conditional relationships. And if we look at a single decision tree, it is defined by splitting nodes with either conditions for categorical or non-categorical features, leading a data point down its branches into a leaf. And to give an example of such an evaluation and to stick with variational autoencoders, we may find a number of encoder layers to be smaller or equal to 3, and the activation function to be in the subset of ReLU or tanh, leading us to the left leaf of this particular decision tree, which will give us an indication of what we can expect for the loss of our validation data set. And then given a tree ensemble, we can determine active leaves for all decision trees. And when we project multiple data points into the leaf space, this allows us to define correlations between them by looking at their leaf overlap. It can actually be shown that this leaf overlap is a valid non-stationary and supervised kernel, and we can maximize likelihood to determine its hyperparameters. And when performing Gaussian process inference, we get a piecewise constant prediction for mean and variance of our surrogate model, which you can see visualized in this slide. And we can then use mean and standard deviation and combine them into an upper confidence bound acquisition function, which we can use to determine the next promising query point. And you can see this on the right-hand side of this slide. So in order to optimize this sort of acquisition function, we propose a mixed integer second-order cone formulation, which can be solved with either open source solvers or commercial solvers like Groby. And to include the logic of the tree ensemble and to link the tree splits to continuous variables, we deploy existing formulations from literature. And you can find more details about the acquisition function optimization in our paper. And for us, this closes the Bayesian optimization loop and allows us to determine new promising black box function queries. And if we have additional input constraints, we can then just simply add them to the previously defined optimization problem formulation and guarantee that we only get feasible black box function inputs. We include an extensive numerical comparison in our paper, and for one of the benchmarks, we even re-implemented the previously mentioned variational autoencoder tuning task from literature and compared our approach to existing algorithms. And for methods that don't support constraints, we added constraint penalization to the black box output to make them aware of input restrictions. And as you can see in the figure, we show that our approach consistently outperforms existing approaches from literature. So in summary, the strengths of our approach are that we can handle various variable types and that we deploy global acquisition optimization that allows for additional known constraints. Some of the drawbacks are that solving such optimization problems is still an NP-complete problem, and parametric tree models may require manual tuning for better performance and may not be a good fit for the underlying black box function. Finally, I would like to thank our industrial collaborators, BASF, my supervisor, and everyone involved in the project. And you can find the code implementing this research on our group's GitHub repository, and will also soon be added to our open source tool, Endmoot. So thanks a lot for your attention.